Last time we talked about how to determine type of bonding based on electronegativity. We're just going to review how to determine the type of bond based on the type of element you have. So if you're talking about ionic bonds, it's a metal with a nonmetal, and you know that the electronegativity difference is about 1.7 or greater. Metallic bonding, we're not even looking at electronegativity difference because you're just looking at metals, something like just pure copper or aluminum. And then for covalent, which is also called molecular bonding, that's nonmetal with a nonmetal. So you're looking at the right side of the periodic table, the right side of that staircase where you have things like nitrogen, oxygen, chlorine, and so forth. Now, starting with ionic bonding, you know that the negative electronegativity difference on that has to be greater than 1.7, and it is a metal with a nonmetal. So nonmetals are ones that have higher electronegativities than metals, because remember that they really want their electrons and they're all trying to achieve that octet. So looking at ionic bonding, if you're looking at the electron configuration, which we looked at last unit, you know that all these elements want to have a noble gas configuration. And a noble gas configuration is one where your valence electrons, your outermost shell, is complete. So like the 1s2, 2p6. So in the case of sodium, it also has a 3s1 outside. And if it can just transfer this over to the chlorine, then sodium would have its 1s2, 2s2, 2p6, and remember this is a neon. And then chlorine would have, so once it adds on that, then this becomes a 6, and remember this would be an argon configuration. So both of them, by transferring, would achieve their noble gas configuration, which is the stable configuration that they're looking for. Now, let's look at another one. So what if we had something like magnesium, and magnesium wants to bond to oxygen? So now go to the periodic table, find magnesium. You're going to find magnesium in group 2. So what does that mean? You know, group 2 means magnesium has 2 valence electrons. So we're going to show those with these little dots. So each of these dots is an electron. Then we're going to find oxygen on the periodic table. We're going to move towards the right side because oxygen, remember, is a nonmetal. And we're going to find oxygen in group 16. Now, that means it has 6 valence, remember? So we're going to put those dots, 6 of them. Now, what does oxygen want to do? Remember, oxygen is an electronegative element. So oxygen really wants 2 more electrons to have that noble gas configuration. And magnesium wants to lose its 2 electrons because it is a metal. So all that's going to happen is the magnesium electrons are going to transfer over to the oxygen. That means magnesium loses 2 electrons, which makes magnesium 2 plus. Oxygen gains 2 electrons, which makes oxygen 2 minus. 2 plus 2 minus, they're going to cancel each other out, because remember that when you form a compound, the compound is going to be neutral at the end. Okay, let's try one more. Let's say we want aluminum to react with chlorine. Remember, aluminum is a group 13 metal, so that means what? 3 valence electrons. And chlorine is a halogen, which has 7 valence electrons. Now, when the transfer is complete, all elements that are going to either lose or gain electrons have to reach the noble gas configuration. So, once aluminum transfers over one, aluminum is not stable yet. So what you do is you draw a second chlorine. By the way, you can draw as many atoms as needed of the same kind in order to make them stable. And then so you still have one more on the aluminum outer shell. So you bring in one more chlorine. And so now what happens? You have aluminum, 3 plus, and you have 3 chlorides, 1, 2, and 3. When we write the formula, it's AlCl3. So this 3 represents these 3 chloride ions. So ionic compounds are solid at room temperature and they form crystals. So these are your positives right here, the purple ones, and these are negatives. So this is sodium chloride. So all the positives are surrounded by the negatives. All the negatives are surrounded by positives. That's the crystal lattice. So it is a very, very, very strong structure in terms of boiling point, melting point, and all that. But it is a very brittle compound. So why is ionic compounds brittle? When you shift any of these rows, so think about these rows right here, right? So you have a negative, positive, negative, positive, negative. So as long as it's set up this way, all your negatives are surrounded by positives, all your positives are surrounded by negatives, which is great because that's maximum attractive forces. But what happens if any of those rows shift is that you would only have repulsive forces. When that happens, it falls apart. That's why ionic compounds are brittle, but they have very high melting points, and this is because of the crystal lattice. They're crystalline solids. They conduct electricity only when they're melted or dissolved. We'll talk about that in a minute. And they're soluble in water. So when you add sodium chloride into a container of water, so here are your water molecules, sodium chloride dissolves, so that means the chloride and the sodium, so the positive and the negative, separate from each other, and then the water molecules surround it. That's solubility. So once it dissolves, then it can conduct electricity. So it has to be melted or dissolved. Melted is really difficult for sodium chloride because the melting point is very, very, very high, but it is a lot easier to dissolve it. And if it's dissolved, if it's soluble, which all salts are soluble for the group 1 and group 2 salts, most of them are soluble. And that means when they do dissolve in water, like the alkali metal salts, so sodium chloride, lithium chloride, or lithium fluoride, or sodium fluoride, any of those are soluble. And when they dissolve, then they can conduct electric current because the ions separate from each other. And remember, electricity is flow of electrons. So if you have ion separation, you can have flow of electrons. They're all solids at room temperature because they have that crystalline solid. And it's really, really hard to melt them or boil them because of the fact that they have that crystalline solid. And again, the one way to test if you're dealing with a molecular compound or ionic is if you dissolve it in water, does it conduct electricity? So the third type of bonding that we're going to talk about is metallic bonding. And metallic bonding has to do with just metals, and the metals are cations, and the valence electrons of metals are what are called C of D localized electrons. So what does it mean something to be delocalized? That means they're just surrounding. So these positive ions right here, the positives are here, are the nucleus, and the little red dots represent the floating electrons. So as you can see, the electrons are shared between all of the metal atoms. So that's what the C of delocalized electrons mean. So by having that, all of the properties of metallic compounds exist because of the C of delocalized electrons. That includes metals are malleable, they're ductile, they conduct heat and electricity, so what makes them malleable? What gives it the ability to be hammered into thin sheets? That's malleability, by the way. Remember, it's hammered into thin sheets is because it's so easy for any of these atoms here, to just slide past each other without a problem. Same thing with ductility. Ductility is the ability to turn into wires. And heat and electricity conduction, again, has to do with the fact that there are all these sea of electrons here, the pink here. The sea of electrons allows for electricity and heat to be conducted because you can have electrons easily flowing through it without a problem. So the three kinds of compounds and three kinds of bonds. The three things we talked about so far is we've talked about covalent, we talked about ionic, and we talked about metallic. So covalent compounds are between nonmetals. Ionic is between a metal and a nonmetal, and metallic is just metals. So you need to know what forms each of them and what kind of properties that they have. So covalent compounds have lower melting and boiling points. Ionic compounds have very high melting points, and metallic varies. With metallic compounds, you can have low melting points or high melting points. So something like mercury is liquid at room temperature, but copper requires a lot more heat in order to melt. So if we have to compare and contrast covalent, ionic, and metallic, there are a few things we would use for that comparison and contrast. So we're going to talk about types of elements involved, conductivity, melting point, state at room temperature, so let's make a table where we can do this. So this is what you're going to do, and this is part of the assignment that you're going to turn into me. So you're going to, this is part of your notes that you're going to put on my JAG by the end you're done today. So you're going to make a table. You're going to put metals, metallic, covalent, and ionic. Then you're going to put these properties: types, conductivity, melting point, state at room temperature. State at room temperature is like solid, right? You can say something like, for metallic, you can say solid except mercury, right? And then you pick another property that we haven't talked about here. And so you're going to make this table along with your notes, and that's going to be part of the notes that you post, you submit on my JAG. You can do it as PDF, or actually do it as PDF. That's the easiest way to do it. So go ahead, and once you're done with the notes, under 11.9, so this is going to be 11.9 notes assignment on my JAG. Okay, so the notes that you took as I was talking about all these things, along with this table that should be in your notes, that's going to be submitted under 11.9. So that's it for today. That's all the notes I have for today. You're also going to get a worksheet now from your sub, and you will also complete that, and that we will talk about tomorrow on tomorrow's screencast. All right, have a great day.